So Aileen O'Donoghue is probably one of the biggest local celebrities we've had here. Certainly the most famous astronomer. You may have heard her recently on NCPR with her regular monthly segment. I know I certainly look forward to hearing that. You may have also heard or seen her doing one of many eclipse talks around the county. I know she's been very busy the past few months. So we're very grateful that she took time out of her busy schedule to be here with us for the first time, her debut at SLCHA. Aileen has been teaching physics and astronomy at St. Lawrence University for many years and sharing her love of the night sky with the community for just as long. She received a Bachelor of Science at Fort Lewis College and a Master of Science and a PhD in physics at the New Mexico Institute of Mining and Technology. Aileen's research is primarily centered around radio astronomy. She studies galaxies using observations from the Arecibo and Green Bank radio telescopes. So rather than invite Aileen here for yet another eclipse talk, we decided that being a historical organization, we'd ask her to reflect on the eclipse. So it's still an eclipse talk. It's just happening after. So she can put it in context with its historical significance, and also let us know about all the other exciting things we can look forward to in the sky. So please join me in giving a warm welcome to Aileen O'Donoghue.
And let me say hello to the, let's see, I can't, oh, I know, that's on this one. Welcome. Let me say, okay, and get rid of that. Dandy. All right, I'm always grateful for the invitation. I really do love talking about the sky. And hello, Zoom audience. I'll try to remember to stay on this side. I'm always telling the university that, you know, I teach for free. They have to pay me to grade. And so this is truly what I love doing, because I'm so excited about the sky, and to have other people to tell about it is just, you know, even better. So yeah, let me talk about everybody saying, okay, we had the eclipse, now what? And yeah, I was listening to some conversations about the eclipse. The peepers came out, insects came out, peepers didn't come out. You didn't get insects, I heard. I was on the quad at St. Lawrence, so I didn't get insects. We did have dark. And did you notice that up until the diamond ring, it's daytime, right? It doesn't get dark until it's total. And so I'm going to talk about some previous eclipses. And so keep that in mind. So anybody have anything they want to say about the eclipse? I mean, was it just totally cooler than you expected?
Yes.
Yes. Yes. And that's, you know, when I was going around giving talks and people saying, well, we're 98, we're going to, you know, it's like, no, totality is very different. So now I'm glad to have a whole bunch of people who know totality is very different than even 99.9%. So here's what I hope to do. I'll talk about some solar eclipses, the eclipse of the peacemaker. So I'll talk about the Iroquois, the Haudenosaunee, I don't know how to say that correctly, so I say Iroquois Confederacy. And then the totalities in Canton that we've had, the most recent one, well, the most recent one is 2024, but the one before that was 1569, and then we'll get another one, 2399. So make hotel reservations now. And then some future sky events, things to keep watching for in the sky, because it changes all the time. We live in a very dynamic universe. So the Haudenosaunee Confederacy, and I got this sentence fragment from this paper, How a Solar Eclipse Helped the Haudenosaunee Confederacy Forge the First Known Democracy. And of course, there are elements of our Constitution that come from their agreement and their lived experience of peace. And so this is Art and Sciences Syracuse.edu. So you can probably just Google how a solar eclipse helped the Haudenosaunee and find this article. I also can this URL will get you there. And so the Seneca were the last Iroquois nation to join the Confederacy. And this article claims that there was a very violent episode, and that it stopped when the sun darkened. And so this article suggests it was an annular solar eclipse in the year 909. And another one that I read suggests it's the eclipse in 1142, which is total. So let's look at those. So this is one of my go-to sites. Oh, I'm sorry, I didn't put the URL. This is the World Atlas of the 5 Millennium Atlas of eclipses. This is by Fred Espenak at NASA. And if you email me, I can send you the link for this. And so what this shows is these are the annular solar eclipse paths from 901 to 920. I covered that up with this little bit of information. And so the totals are these blue arcs. And like ours, this is the moon's shadow moving across a sphere. So that's why it's always an arc. And so here we had a total eclipse that went up through Canada and into westernmost Africa. There was one that was way up on the Canadian islands. And then there was this annular eclipse that came through western New York. So if we look at this is another one of my go-tos. This is by Google Maps by Xavier Joubier. He's a French astronomer, and he puts all these eclipse data onto Google Maps, so you can zoom in on wherever you want. So I zoomed in on the Ganondagan historical site, which is in Victor, New York, just south of Rochester. And so this is where it is. Here is the path of annularity. We had an annular solar eclipse back in 1994. And some of you may remember that. It was a big deal for us at St. Lawrence. And like just before totality, it didn't get dark, although we were at 90% of totality. So when we look at this, here's the data for this. And let me zoom in so you can read it. And it was an 88.9% obscured sun. So it was, 90%, not totality by any means. And so this is what a simulation of what the sun would have looked like in the middle of, quote, totality. It's not quite centered because they're a little bit off the center line. Would they have noticed? Yeah, they would have noticed, because as the partial eclipse got closer and closer to totality, the light got weird, right? And one of my students said everything looked gray to him. Another person said everything had an orange tint. And it's because your cones in your retina are the ones that pick up color. And so they respond in their own unique way. And so they would have noticed that the light was weird, but it wouldn't have been dark. So is that enough to cause peace to break out? I mean, it could cause a war, but causing peace, I mean, that's a much higher lift. And so let's look at the total eclipse of 1142. And so again, here are these maps. And here, August 22nd, 1142, we had a total eclipse that went through southwestern New York. Right? There was another one here on 1151 that went through the rest of the country. And so these were the eclipses from 1141 to 1160. And if we zoom in on this one, so there is that state historic site, and there's the path of totality. So they have that historic site saying that's where the agreement was signed. If that's where the peacemaker was, he was not within totality. So I don't, this is something for the historians to figure out, is which of these eclipses and where was the peacemaker, or where were the Seneca when they saw this eclipse. Because for this one, if we bring up the data and then make it large, so this was 99.3%. And that's 99.3. One of the links I found when I was Googling trying to find out what's 99.3% of totality like, I found a place just outside of Cincinnati. And this was on a news report. This is just a screenshot of their report, and here's the URL. And so there was the people in Cincinnati were saying, oh, well, we're at 99 something. I mean, why go up? Why drive upstate? I mean, yeah, we're going to be good. And they showed that this is what it was going to be in Cincinnati. And this was, 20 minutes north. And it's very different. It's day and night, partial and total. And so is that enough to cause peace to break out? Yeah, I don't know. And this is where, we have to ferret out the history. So totality is in Canton. And so let's look about these. So generally, there's about 400 years between total eclipse events in a given location, but that's just an average. So the last totality in Canton was on September 10th, 1569. And so that was 455 years ago. And then this year on April 8th, and then the next totality in Canton is in 2399. So that's 830 years. This was one event in 830 years. So it was really a once in 10 lifetimes event here in Canton. And there were people, I've heard from people who were, in their yard on Route 11 or in their yard on the May Road in Potsdam. And there were people driving during totality. They were just in their cars driving along. It's like, what? Really? It's just, are they that unaware? Are they like, geez, that must be a dense cloud coming in. It's a storm. Let's go fast. There were local people who just, I guess, didn't get the memo. A 1 in 10 lifetimes event. They probably had kids in the car too, I wanted to see the eclipse. And so here was the 1569 eclipse. It happened near sunset. And so here is Canton during that 1 minute and 5 seconds. So apparently they did know what eclipses were by 1569, so they weren't terrified. And so from 5:29 to 5:31 p.m. was that eclipse. And the shadow swept down this way out of Canada. Here, is our April 8th experience, and it was just amazing. I was in tears the entire totality. I was just, and part of those tears was utter relief that it wasn't a dud, because I'm always talking on public radio about some fantastic, cool event to watch, and then it's a dud. It clouds up. It doesn't happen. So I may be saying this to you about Solar Max and T-Core Board. So here, the next one, this is going to be great. 5 minutes and 11 seconds. And I don't know what it was like for you, but those 3 minutes went by in a snap for me. It's like as soon as it was dark, I could see that the light was coming back from the west. And it's just like, no, I wanted to hang on to it. And so now I want to go become an umbraphile and chase eclipses around the world. And if you're interested, the next one is 2026 in Spain. But it's under 2 minutes. It's northern Spain. In 2027, it goes across North Africa. The longest duration is in Luxor, Egypt. And so that's going to be like 7 minutes. And then Australia in 2028. So, you can always find an eclipse most years. And there are eclipse cruises if you want to be in the ocean. So I should see if I can, work some of those cruises. And so here again, Canton will be near the center of totality, and all of northern New York. Oh no, this is 2399. All of northern New York again will get the eclipse. So this is, that's something to look forward to. Maybe the kids that were in those cars, they didn't get it. All right. So what future sky events do we have come in? It's only 12:15. Geez, I usually talk for so long. So, what's future events do we have coming? Well, we have Solar Max coming. And so this is when the activity on the sun peaks. And here you can see, this is an image of the sun today. We have satellites and ground-based observatories that look at the sun 24/7. So you can always, oh yeah, he's putting on his eclipse glasses. Yeah, there's no UV coming off the screen. You're fine. And you can see there are sunspots, all right? There's a bunch of them here. This image is from spaceweather.com. And this is one of the websites you might want to start going to regularly to look at, because from spaceweather.com, you can also look at what are the auroral predictions for your area. And there's lots of information on that. And actually today, they were showing that the time signal. So WWV is the national time signal. When I was a young astronomer, before we had cell phones and internet, we had a little radio that it ran the WWV broadcasted at 10, 5, 10, and 15 megahertz. So it was a special little radio you got, and you tuned it in, and all it did was give you the time and warnings about solar storms. And so I would observe all night, and it was how we kept time. We would listen to WWV. We were doing 10-minute exposures, and we would listen to it to know when to start and when to stop, and to record the times when we did our observing. And so what you'd hear was on the tone, 4 hours, 37 minutes, coordinated universal time. And then it would bong, and then you'd hear tick, 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 tick. And then they'd say something about warnings and, of a solar storm or something. And then on the, at the tone, 4 hours and 38 minutes. So, and it turned out during the solar eclipse, that signal got shifted in frequency, because there's a layer at the top of the atmosphere, which is called the ionosphere. And ions are atoms that have lost some of their electrons or gained electrons. And so at the ionosphere, there are a lot of collisions among molecules, and they lose their atoms, so they're ions. And this ionosphere interacts with radio waves, and it's what makes radio waves bounce around the surface of the Earth. So at night, I don't know, some of you may be old enough to remember this, but at night when you were tuning in your AM radio, you could tune in very distant radio stations all of a sudden, and if you wrote to them, they'd send you a card saying that you pulled in their radio signal. So this ionosphere is very important. And under the shadow of the moon, this ionosphere, since it was so cold, it changed and it moved. And that motion shifted the frequency of the WWV signals. So that was one of the weird effects of the total eclipse. So that's on spaceweather.com. If you want to understand more, just Google it. So we have these sunspots. And one of the things I try to emphasize when I show people images of the sun is just how big it is. It is huge. It is the diameter is 100 times that of the Earth. So let's bring the Earth in on this. There's the Earth. Oh, let's scale it. That is the actual scale of the Earth. It's dinky. And here are others. There's an Earth, there's an Earth, did you see them all fly in? Those of you online, I hope you'll be able to see them. And they're dinky. These sunspots are huge. You can throw the Earth in, and these aren't the biggest sunspots. Some are much bigger, and I'll show you some bigger ones today. So the sun right now is getting more active. And so what's going on? Well, the sun and every star is a nuclear explosion contained by gravity. So in the center of the sun, it is fusing hydrogen to helium because it is so dense and it's so hot, and these nuclei, the protons and the neutrons get crammed together to go from being hydrogen, which has one proton, to helium, which has two protons and two neutrons. And that's what's happening. It's a nuclear explosion. That's what the hydrogen bomb was, is it fused hydrogen into helium. Not very much, but it was enough to blow up the atoll and just remove it from the face of the earth. So that's what's going on in the sun. And explosions, well, that nuclear reaction is trying to blow the sun up. But gravity, all the outer layers of the sun, gravity is trying to squeeze them in. And eventually gravity will win. Because gravity is relentless and it'll run out of hydrogen fuel. But since it's an explosion, there's particles flying off the top of it all the time. All right, and it's called the solar wind. And so this solar wind gets steered. Those of you on Zoom, I'm pointing at the picture on the left. So these particles stream at the Earth, and the Earth has a magnetic field, and it's like the magnetic field of a bar magnet that immersed in the Earth. And particles, the ultimate picket line is magnetic field lines, because charged particles really don't want to cross magnetic field lines. They would rather go along them. They get caught by the magnetic field and they actually spiral along the magnetic field lines. So that's why all these charged particles from the solar atmosphere, they get, and the corona, by the way, was part of this solar wind. It's the origin of the solar wind. So those of you who saw the corona, you've seen the base of the solar wind that is constantly blowing at Earth and constantly hitting our magnetic field. And notice it gets deflected around the magnetic field. Some of the particles get steered toward the poles, and that's where we get the aurora borealis. Because the aurora and the borealis and australis, these are where those charged particles come into the atmosphere and collide with particles in our atmosphere. And then they knock electrons off of those particles, or they knock electrons to higher energy levels. And then we see the light when the electrons rejoin or cascade down to lower energy levels. That's why we see the light in the aurora. And so here is an image of an aurora. And this is from 2003. We had some fantastic auroral displays here in 2003 and 2004. Did any of you get to see those? I mean, we were looking up the rays 20 years ago. It was fantastic. Notice how this is kind of striated. There are lines there. That's the signature of the magnetic field lines, because the particles get caught on those. And so you have more glowing particles along those lines. And so that's what we saw. So let me show you. I got to go to the computer now. So over here, if I go to this, I can start this little video. So is it going to run? Oh, don't tell me it won't run. Media not found. Oh, geez. I don't know why that happened. Media not found. I don't know why those. I'm sorry. They work on my computer. So these are videos that work on my computer. I don't know why they're not working here. But what you would see is this is the base of this big arc of plasma is sunspots. And this shows this burst of material coming off the sun that's called a coronal mass ejection. And it comes flying at Earth. And what happens here is when it collides with Earth, it smooshes the front of the magnetic field, and then it gets steered around, and some of those particles get flung back toward the poles of the Earth. And so this just shows the process that when we get bursts of material off the sun, that these cause the auroral displays that we see. Those are what caused this event in Croatia. So here, this is part of the energy that comes to us from the sun. And so up there, so that video is working. That's a GIF. And so you can see that's a huge sunspot. That one was about the size of Jupiter. And so 2003, 2001 was solar max. So in 2003 and 4, we were getting these huge sunspots. So here's a sunspot, the base. It's a little cooler than the rest of the surface of the sun. If you took a scoop out of it and put it, away from the sun, it'd be blazingly bright. But it's a little dimmer than the rest of the sun, which is why it looks dark. And here, this is from a spacecraft called SOHO, the Solar Heliospheric Observatory. It's from 2003, October 28th. This little white circle is the size of the sun. Like us, when a spacecraft blocks the sun, it has to block more than just the disk. Because if something shifts, it could blind itself and fry the instrument. So they have to block out more than the sun. And what we're seeing in this is a burst of material from the sun called the coronal mass ejection. And it actually came at this detector. When you see all those speckles right at the end, that's because the particles from the sun actually hit the detector. And so this was one of the huge bursts that led to the really spectacular auroral displays that we had in 2003 and 2004. And so this was the sun then. Look at the size of those sunspots. And I had my students, we had these during a class day. And so I forgot what the date was, but I took my students out, we set up the telescope, and one of my students looked in the eyepiece and says, "It's a dot." Yeah, it's a dot the size of Jupiter. And so I tell my students that here, you could actually see it. This is a photograph of the sun. That's how big that was. And so it was just these, 2001 to 2003 was fantastic. This was 2004. So what happens? Why do we get sunspots? Well, they're basically magnetic hernias. So the sun has a magnetic field, just like the Earth does, and it's a bipolar field. So these big loops come out. And here, the thing about the sun is that the equator rotates faster than the poles because it's not a solid body, it's a gas. Sun is a mass of incandescent gas. You guys remember that song from long ago? And so the equator goes faster and it starts wrapping up these magnetic field lines around the sun. And so then they start bulging out. And so that's why I say it's a magnetic hernia, is this magnetic field line bulges out and it carries with it this plasma. All right, a plasma is a hot ionized gas. And so it carries this hot ionized gas up out of the surface of the sun. And if you look at videos of the sun, just Google surface of the sun videos. And NASA has amazing videos about this just really active, broiling surface of the sun. And so these get bulged out. And so this is showing this has a south pole and a north pole. That doesn't really matter. But as it comes out, these charged particles that like to be steered by the magnetic field, they come leaping off the sun. And to leap, they have to take energy from somewhere, and they take it from the surface of the sun. And so that's why the surface of the sun is cooler, where these particles are leaping up to follow the magnetic field lines. And so here, this shows it a little more like a hernia. So this is bulging out. And when we look at images, here's an actual image of this. And you can see this is a magnetic bulge. Again, the striations, the lines here show this is a magnetic phenomenon. And we also have instruments that can measure the magnetic phenomenon. And so the particles are running up. That's why the sunspots are darker than the rest of the surface. And so some of these then form these massive bunches of particles. These are hot ionized particles in the coronal mass ejection. The corona is what we saw, right? And it's a chunk of that hot atmosphere that gets trapped actually by these magnetic fields, because the magnetic fields underneath here, they don't just sit there. they're in a on the boiling surface, so they twist around. And if they twist, they can cut all this material off and fling it at the earth at like 2 million miles an hour. I mean, these things are booking when they come. And so that is the origin of some auroral displays. And this, it shows here, it shows the twist here and these things and these particles bulging out. And so we are coming into solar max again. So the number of sunspots varies very regularly. Over about 11 years, you go from a maximum number of sunspots to a minimum number, and then you go up to another maximum and then another minimum. And so this is the record of sunspots over the past 400 years. And the record goes past 2000. I just haven't updated this particular plot. But we did have, back in 1650 to 1700, there was a law. And people were actively looking for sunspots. Among the people looking for sunspots was Galileo. Some of these data, these counts, are Galileo. And he looked at the sun through thin clouds. All these old astronomers, and they all lost their eyesight in old age because they looked at the sun and to look for sunspots. But there were no sunspots for 50 years, and then it started this regular variation again. And this is just the total number. All right, so here in the 50s, all right, we got up to 200. That was a huge maximum. So here is where we are today. So this is 2014, 16, 18, 20, 22, 24. So we did have a solar max in 2013, 2014 that was kind of, we didn't get any great aurora. There weren't that many sunspots. The sun was very quiet. And it took a long time. It got down to a minimum. And astronomers were thinking, geez, are we going into another Maunder minimum? All right. And one of the things that happened with the Maunder minimum is that this was the time when it was cold in Europe. Right? Probably some of you read Hans Brinker in school. Did you guys read that? Yeah. Yeah. And he was a skater in Holland on the canals. Canals in Holland don't freeze. Not now. But they did then. And so people made a connection. Oh, when we don't have sunspots, it gets cooler. So some of the anthropogenic climate change deniers are saying it's all the sun, but because the sun has been kind of quiet, all right, in this century. But we're ramping up now. So it's been quiet, but the temperature is going up. So that connection doesn't work, but you will hear that it's all the sun. So here, look at that. Oh, yes, we're above what it was, what the predictions were. So maybe we'll get some more great auroral displays coming up. Check on spaceweather.com, see what the sun is doing. And so, yeah, maybe there's more auroras coming. And this is the URL, by the way. The www Space Weather Prediction Center we have, people going to work every day who are measuring the solar wind and looking for coronal mass ejections and events that will bring us auroras. Because it turns out the aurora is not always friendly. Any of you were here in 1989, we had an amazing auroral display. I wasn't here. I was back in New Mexico trying to finish my dissertation. Yes.
I think that's the one I saw. And there was one night I was picking up milk in Lisbon at night, and the farmer came out with me and showed it to me, and we just stood outside and watched
it. It was very red. It was very powerful. And you know what it did? It knocked out all the power in Quebec.
Oh.
Because, it did. Complete blackout. Yes, it was amazing. And it caused Hydro-Quebec, all their long power lines. The aurora is a magnetic, an electromagnetic event. the magnetic field of Earth is very active. And you have a lot of charged particles running around. And all you need to do to make a magnetic field is move charged particles. You make a current, and that makes a magnetic field. And if you have a changing magnetic field, that induces a current. All right. All of our power plants in the world, all they do is turn a coil in a magnetic field. And that creates electricity. So anytime you have a current moving with magnetic fields, or magnetic fields moving around a wire carrying current, you're going to create more current. And it created so much current in the wires of Hydro-Quebec that it blew all their transformers. And the entire province went dark. And so that was, and this is why we have people watching 24/7 to see if these coronal mass ejections are headed our way. And so, yeah, so let's look at the last major solar storm we have recorded in US and Europe was in 1859. This is something we ought to look for records of here in the North Country in the newspaper reports. Because this one, they had just strung telegraph wires all over the US and Canada and Europe. And like Hydro-Quebec in 1989, the auroral display was so powerful that it caused currents, huge currents to flow in these wires, and it shorted out at the supports, and the poles caught fire. So in scientific circles, where solar events are discussed, the occurrences of September 1 to 2, 1859 are the stuff of legend. Many of Earth's inhabitants realized something momentous had just occurred. Telegraph wires in the United States and Europe spontaneously shorted out, causing numerous fires, while northern lights, all right, the aurora borealis, was documented as far south as Rome, Italy, Havana, Cuba, and Hawaii. And the same thing at the South Pole. And so if we had this today, all of our satellites, all our cell phone networks, these are all electromagnetic signals, right? I'm surprised maybe there was some Doppler shifting of cell phone signals with the solar eclipse, and none of us noticed because of, yeah. So it's just, if we had a major magnetic storm, it would cripple a lot of us. Because the internet could go out, GPS could go out, all of this. And I heard that the Naval Academy had stopped teaching celestial navigation because they thought, well, we have GPS. And then somebody says, yeah, what about a coronal mass ejection? Or what if the power goes out? Oh, fortunately, the people who had taught celestial navigation had not yet died. So they brought them back. They're now teaching celestial navigation as a backup. But this could be really disruptive if we have a major coronal mass ejection. So, what would happen today? Well, all we can do is wait. Wait and see. That's what we can do to see what happens as we come towards solar max in 25 or 26. So, the other cool thing that may happen, it's supposed to happen this summer, but we'll see. This may be one of the duds. But it's T Coronae Borealis. So let me show you the eastern sky tonight. This is about 11 p.m. so I could get the constellations up. Oh, what did I do? Here it is. All right, so there's our friend, the Big Dipper. So if I take it off, can you find the Big Dipper now? All right, so there's the Big Dipper. And if you follow the pointer stars, they point at Polaris, which is at the end of the handle of the Little Dipper. And so then if you go farther, there's Cassiopeia. Most of us recognize Cassiopeia, the cosmic W. And then her beloved spouse, Cepheus, the king. She was the queen of Ethiopia. He was the king. And so the king looks like a house that a kid would draw. And they got distracted at the bottom corner and drew a little triangle. So here, in between these are called the guard stars. The two stars at the end of the handle of the Little Dipper are called the guard stars. Furcad and now I can't remember. I'll remember in a minute. But these are the guard stars. Between them and the middle star in the handle of the Big Dipper, which is actually a double star, if you look at it carefully or even with binoculars, it's two stars, Alcade and boy, I can't remember the name. And some of the native people called it horse and rider, and Alcor, yeah. Can't remember. I don't know what my brain is fried. Must have been the corona. Yeah. And so anyway, that star right in between them is called Thuban. When the Egyptians were building the pyramids, that was the pole star. It was the star that the axis of the Earth pointed at, because the equator of the Earth wobbles over about 26,000 years. So the pole star makes a big circle around the sky. Right now it's Polaris. It's also been Vega, which I'll show you in a minute. So it was Thuban, and now it's Polaris, and it's going around this way. It'll move through Cepheus. And so from back at the Big Dipper, if you follow the arc of the handle, you can make an arc to Arcturus. And Arcturus is a very bright star. It's hard to miss it. So there's an Arcturus. And if you continue, you can make a spike to Spica. And Spica is here in Virgo. And so Virgo is one of three women in the sky. All right. You have Cassiopeia, who's actually chained to her chair because she lipped off at the sea nymphs and said her daughter Andromeda was prettier than any of them. Well, that pissed them off, and they got their pal Poseidon, god of the sea, to go and say that he was going to have Cetus, the sea monster, go and destroy the kingdom of Cassiopeia and her husband Cepheus. Well, Cepheus ran to Poseidon and said, "Oh, please, no, what can I give you?" And he says, "Well, chain your daughter to a rock and have Cetus devour her." And he said, "Well, okay." Yeah, great dad. So anyway, so the women in the sky, there's Cassiopeia. Over here, there is Andromeda, who's chained to a rock. And then Virgo, who's standing there with a sheaf of wheat. It's like the women in the sky really don't get treated very well. You know? So that's why I'm on my personal campaign. You may have heard it on North Country Public Radio, to make it Mother Orion, because Orion's sword, yeah, we know what they meant, but it's full of baby stars. There's always room for one more, you know. And so anyway, so here is Virgo. But one thing I like about Virgo, it's got a very cool name of a star. Yeah, Zavi Java is up there at the top of Virgo. All right, so in this kind of blankish area, there's some stuff going on. This is a constellation called Coma Berenices, the hair of Bernice. Her husband was, I think, one of the Ptolemies, and he went off to war. And so she cut off her hair and left it on the altar as a sacrifice to bring her husband home alive. He came home alive, so one of the Greeks put her hair up here. Not her hair up here in the sky. And this is nice because there's a lovely little star cluster there. If you get your binoculars out and you look between Zavi Java and the Big Dipper in that area, you'll see this glittery little bunch of stars. And they're hiding a huge cluster of galaxies that's too far for us to be able to see, but it's lurking there. And then here are the hunting dogs, Canis Venatici. So just those two little, you know, it's hard to see these. These are pretty faint, but there they are. Yes.
So that would be more in this.
This is, we're looking to the east, northeast here. Northeast. So here is north, here's northeast, here's east. Yep. I guess this is the east northeast. Yeah. And so, you know, from the Big Dipper, that's, you know, you find your roads to other things. And certainly the arc to Arcturus and the spike to Spica are pretty easy. Yeah. And then down here, just rising, is it's called an asterism. It's not one of the official constellations, but it's a little symbol that people recognize. The Big Dipper is the same thing. Ursa Major is the constellation, but usually all we pick out is the Dipper. And so down here, here is the keystone. It's harder to see without the lines. There's that. And these are actually the hips of Hercules. And so Hercules is here. He's the kneeling one. So he has one leg, he's kneeling on one leg, and the other leg is up, and he's upside down. He hangs upside down in the northern sky. And so here are his arms. So this one he's holding a club, all right, and the other one he's holding a shield. So we see that here. And so that's Hercules, and then Vega is very bright. It's rising in the northeast late at night. And so I show you these so you can find Boötes. Boötes, which is the constellation for Arcturus, it looks like an ice cream cone. It's actually a herdsman, but I don't see it. I see it ice cream cone. So here's the cone, here's the ice cream, and there's even a little drip. And the name of the drip is Muffred. So this little drip is Muffred. And so in between is Corona Borealis. And it's this lovely little circlet of stars. And once you see it, you can never not see it. It's like, oh yes, you know, it's really obvious. And so if we take these, if you have Arcturus and you're coming toward Vega that's very bright, you've got this keystone and then the circlet of stars that is Corona Borealis. And so that's the northern crown. And that is where T Corvor is. And you can't see it. It's too dim to see. But a couple of times in the past that we have recorded, it has, oh, and here close to it is the head of serpents, a little triangle that might help you if you're looking for it. But when it gets bright, you should be able to see it. And so what's happening with this star? Well, there are people who are always watching the stars, the American Association of Variable Star Observers, AAVSO. They're mostly people with small telescopes in their backyards, and they do very good astronomers. My colleague at the Vatican Observatory, Chris Corbally, he was here for the total eclipse. All right, he's a Jesuit priest and an astronomer. He's a top-notch astronomer, much better than I am. And he works with a group of backyard astronomers. He calls them small telescope astronomers. They're not amateur astronomers. They do very professional work. And so the American Association of Variable Star Observers is a bunch of these people. And this was in 1946. So this star suddenly brightened. You can't see it. And then all of a sudden people could see it in 1866, 1946, and maybe 2024. Every 80 years, we're due. And there people are looking in historical records to find brightenings before 1866, because it probably did. So here we can see, so here's 44, 45, 46, 47. So this star was very dim. It got even dimmer. And then boom. All right, this is apparent magnitude. And it's always upside down. Because Hipparchus, one of the Greeks, he came up with a very reasonable system. He said, oh, the brightest stars, they're number one. The next brightest stars are number two. The next brightest star is number three, which means dimmer stars have higher numbers. So astronomers plot magnitude with, you know, the large positive numbers at the top and the large negative numbers at the bottom. So it went from 10, which is where it is now, which you can't see. The limit of human visibility for the stars is about 6. And you can see it got all the way up to 3, which is about how bright Polaris looks, the North Star. The stars in the Big Dipper are a little brighter than this. And when I show students the North Star, you know, and I point it out, so I say, follow the pointer stars, and that's the North Star Polaris, they're all like, it's going to be brighter. Everybody is disappointed that the North Star isn't that bright. It's not bright, but it's important where it is because the Earth's axis points in. So this will become as bright as Polaris. So all of a sudden in this obscure little constellation, it's like, wow, that it's much brighter. And so this is supposed to happen this year. So let's look at what's happening. So these are two different colors actually, and blue and visible. And here in the blue, all right, there's 22 2022.5, so that's June. And here, and notice, 2023, the brightness starts to fall off. So maybe we're going into this dip that happened in the 1946. And what is it? Well, we've studied this a great deal, and it's two aging stars. Remember I said gravity will win. And it will win when it starts winning. The stars, they run out of fuel, and one of the stages is they swell up huge. When our sun goes through this, it will swell up so large, it will be about the size of Earth's orbit. Not, just 100 times the size of the Earth. It will be the size of Earth's orbit. It will swallow Mercury and Venus. They will just get desiccated and cooked and turned back into dust. So here is a red giant star. It's swollen up because it's in its death throes, and it's throwing material. It bursts material off of itself that ends up in a disk. And immersed in here is this stellar remnant, a white dwarf. After our sun goes through being a red giant, it'll eventually blow off all of its outer layers, and only the core of the sun will be left as a naked little white dwarf star. And they're retired stars. They aren't doing nuclear fusion anymore, but they're hot. And so all they do is hang out and cool off. And it takes them millions of years to cool off. It'd be about the size of the Earth. So imagine something the size of the Earth at, 40,000 Kelvin. It's going to take it quite a while to cool off. And so it's very hot, and this material piles up on it. And here you can just see it immersed in its little disk of material that's piling on it. And so it keeps hitting the same spot, and eventually the white dwarf heats that material up enough that it has an explosion, and it's a nuclear explosion. So it explodes. And this is what makes T Corps all of a sudden as bright as Polaris, is this white dwarf star blowing up this material that has been falling at it from the red giant. And so we can know about the motion from Doppler shifted when we look at the spectra. And so this is the business. This is what, stellar astronomers do, is look at these things over again. So over and over again. So we may get to see that this summer. We're thinking by September is what the variable star people are looking at. So this is coming. Find Corona Borealis. And when you go outside, look, how's T Corps doing? It hasn't blown up yet. So always, as an astronomer, okay, so I had one more slide. Currently, it's too dim to see, and it might become as bright as Polaris down there, past Bodes. All we can do is wait and see, like solar max, and that's the exciting part of astronomy. So, as always, the adventure continues. The wilderness above is always worth watching, because there's always cool stuff going on. So, thank you. All right, I was worried I was going to be too short. Apparently, I didn't do that.
Thank you so much.
Yes, thank you.